Okay, here is lemma 8.6.1. I guess I should have said this is section 8.6. So we have, we're going to let x and y be non-zero and non-parallel. Okay. If that's the case, then one is that I'm going to write it this way. They say z is a linear combination of x and y, so I'm going to write z is c1x plus c2y if and only if, so two f's there, if and only if z is perpendicular to x cross y. So z, and we can write this various ways. We could do the little perpendicular sign, x cross y. Or another way we could say it is z dot x cross y is equal to 0. Okay, so this was that scalar triple product. So, so we have that one, and then 2. It says z is perpendicular to x cross y if and only if z is parallel to, oh, not x cross y. Gosh, I thought, that's odd. Didn't we just do that? Okay. So, yes. Is perpendicular to x and y if and only if z is parallel to x cross y. Okay, and so if we look at these and look at the proofs, I don't think I'm going to go through everything in detail, maybe, but so if we look at 1 in the proof, we need to go, both directions, and so we have, we'd like to show that z, if it fits this, is perpendicular to x cross y, right? So, well, let's assume that z is a linear combination of x and y, and so if we name, say w equal x cross y, I don't know if I really need to do that. And then I say, well, okay, I would like to take z, and I'm checking to see if I get 0 for the dot product. So, so I'm going to do that. So z dot w, well, that's z dotted with x cross y, and now, so then I have, this is equal to some c1x plus c2y, all dotted with the vector x cross y. Now, the dot product, I'll use my dot product properties, and so this is c1 x dotted with x cross y, and plus C2y dotted with x cross y. But back here in the properties somewhere, I can't scroll back because it was on a different page, but it said that that is the 0 vector, or, well, actually, in this case, I guess it's 0 because we're doing the dot product. So we get 0, so this is C1 times 0 plus C2 times 0. And so we get 0. Okay, so that says if z, so if we know z is a linear combination of x and y, then we get the orthogonality there that we wanted. Okay. I was looking at their proof to see what they were doing. They do the other one first, I guess, and they use a. Oh no, they do the 0. Oh no, yeah, so they did it like we did. That they get their 0 that way, okay? And now what their second part, they assume, so right, assume z dot x cross y is equal to 0, right? So now we're assuming this going the other direction. And if that's the case, they say from 8:15. Oh, okay. So they did some preliminary work, and I didn't really look at their preliminary work. They said if they know that the dot product is 0, then they can write z equals r x cross y plus sx plus ty. Right? So they say if z is a linear combination, if it's orthogonal to x and y, then we could have set up some linear combination like this. Well, you know, where are they getting that? And they're getting it from back a little bit. So I'm kind of looking at what they did. And let's see. And so they just start with this determinant. Oh, that's interesting. Okay, so they're taking the determinant of a matrix. They're doing it by rows, actually, but they write it this way. So x cross y, that's the first column, is that vector, x cross y. Then they do a column of x, and then they do a column of y transpose. So it's actually the x cross y is the first row of this matrix. And they're taking the determinant of that, and they say, well, if you look at that determinant, you just get x cross y dotted with x cross y. And that is greater than 0, they say. Okay, so certainly if I take x cross y times dotted with x cross y, that should be strictly greater than 0, since we have x and y are non-zero vectors. Okay, so x cross y will be a non-zero vector, and so so they're pointing that out, that that thing has a determinant greater than 0. And so if that's the case, if that determinant is greater than 0, then if we were, let's see, so it's non-singular. So that's a pretty neat way to show it's non-singular. And then they say, well, okay, if we then were to do solve a problem like, say I did the matrix system, x cross y, x, y, so I've got my 3 by 3 matrix here. Now I didn't do the transpose, so these are the columns. And I try to solve this equals my z vector. Well, there is a solution, they're saying. Okay, so there is a solution, which means in that case z can be written as r x cross y plus sx plus ty. Okay, so that gets us back here. They say, okay, assume this is 0, but also assume then that we can write z that way. And certainly we can, according to all this stuff. So, okay, so we've written z that way. And so if we just do that dot product, so z dotted with x cross y, then we would have 0, because that dot product is 0. And I would have r x cross y dotted with x cross y. Need my dot in there. And then plus s times x dotted with x cross y, and then plus ty dotted with x cross y. Okay, but that's 0, that's 0, and so this is r times the magnitude of x cross y squared, but the magnitude of x cross y squared is greater than 0, so this implies r equals 0, but if that implies r equals 0, then that's where we get the linear combination. Z is some sx plus ty. So there we have the two directions of that first one. And so then the second one, they first assume, okay, z is parallel, so they use a lambda, x cross y. Okay, so we're just assuming z is parallel to x cross y. Then they say clearly, right, z dot x equals z dot y equals 0. In other words, it's clearly perpendicular orthogonal to x and y. Okay, so that was the first part. We got to go way back here and look at. We assume this z was parallel to x and y. Now we need to look at z perpendicular to x and y. And okay, so now assume z dot x equals 0 and z dot y equals 0. We need to show that z is parallel. Well, again, they go back to, well, we know that we can always write z as sum r times x cross y plus s times x plus t times y. Okay, well, so if that's the case, then what I see is that they're saying s x dot x plus t x dot y is equal to x dot z, and that's equal to 0. Now, so we've assumed that. Okay, now where could we get that? Is that let's see. When I'm trying to figure out where to write this. Well, when I did z dot x, right, I ended up with, so I'll write it over here, I guess, x cross y dotted with an x. Okay, but that we know we get 0. Okay, so in that case, then we get 0 from that part, and so we're just left with the s and the t. And then similarly, s x dot y plus t y dot y, which was y dotted with z. And again, for the same reason, if I take my x cross y dotted with y, I get 0. So I get 0. All right, so so we have both of those are 0, and they say, well, okay, so from that means that if we were to take s x plus ty and dot it with itself, no line over the s, ty, and dot it with itself, they say, well, we get 0. Well, where does that come from? Well, if you do that dot product, notice you get s x dot x, you get 2 s plus 2 st x dot y, and plus t, squared, s squared, t squared, y dot y. Okay, so that's what that dot product is. And do we see that here? Well, notice if I multiply through the top here by s, and I multiply through the bottom here by t, I'll get my s squared, x dot x. I'll get my t squared, y dot y, and I'll get the two STs. So if I add then those two equations together, that's where I get this is equal to 0. So I took I took those s times the top equation, t times the bottom equation, added them together, got this, which then we recognize as this dot product. Okay, but if I get this dot product to be 0, the only way that dot product is 0 is if sx plus ty is equal to the 0 vector to begin with, and I know x and y are not parallel, they're independent of each other, and so the only way to make that happen is s equals 0 and t equals 0. Okay, so but then going way back to here, we've just determined that s and t are 0, so z is just r times x cross y. And so it's parallel. So that pretty long proofs, really, when all's said and done, to get those. And we really needed this stuff up here, that we could write z as a linear combination of those vectors as a basis. So, but once we have that, we can get that lemma.